yet they face serious limitations. We identify the primary limitations into three aspects. First, at the feature level, features are often converted into numerical or categorical values for utilization, but they lack reasoning and understanding from the knowledge aspect. This leads to a lack of reasoning and knowledge in feature representations. They struggle to capture deeper semantic feelings or word knowledge associated with items or users. Second, at the interaction level, data sparsity leads to insufficient training for RS models. This cold start problem or long tail distribution severely hinders the model's ability to make accurate recommendations, especially for new users or items. Finally, at the model level, recommendation models according to an embedding and deep network pattern can only capture collaborative signals while ignoring semantic information. This limits their ability to generalize beyond observed interactions and provide explainable recommendations. Now, let's turn our attention to how large language models offer solutions to these challenges. The fundamental strength of LLM is the superior reasoning and comprehension abilities. It has extensive word knowledge and can intelligently understand and process natural language. This directly compensates for the shortcomings we just discussed. At the feature level, the LLM utilizes reasoning abilities and word knowledge to derive textual descriptions for users or items. These descriptions serve as extra features to supplement reasoning and understanding knowledge. At the interaction level, to face the data sparsity issue, some research studies adopt the LLM to derive new user item interactions. At the model level, the LLM can analyze the interactions from a semantic view, assisting the conventional recommendation models. This leads us to the concept of LLM-enhanced RS. In this tutorial, we discuss the LLM-enhanced recommender system, abbreviated as LLM-ERS. It means the conventional recommender systems are enhanced by LLM via assistance in training or supplementary for data, while no need for LLM inference during the service. Existing tutorials and surveys mainly focus on how to use the LLM itself as a better RS, including generative recommendation and discriminative recommendation. By contrast, we only discuss LLM enhanced recommender system in this tutorial, which has been rarely introduced. This pushes the LLM into the online system with a large step by eliminating the utilization of LLM during inference. This design choice is vital for maintaining the low latency required for real-world recommender systems, making LLM-enhanced RIs a highly practical and efficient approach. As depicted in the figure, we categorize these enhancements into three main lines based on the component of an RS model: knowledge enhancement, interaction enhancement, and model enhancement. Knowledge enhancement utilizes reasoning abilities and word knowledge of the LLM to derive textual descriptions for users or items. These descriptions will serve as extra features to supplement reasoning and understanding knowledge, and thus they can tackle the feature level limitation of traditional recommender systems. To solve the data sparsity issue, the interaction limitation, interaction enhancement methods adopt the LLM to derive new user item interactions. The LLM can analyze the interactions from a semantic view, so some model enhancement works have tried to make use of the LLM to assist the conventional recommendation models, addressing the model level limitation. Our first main category of LLM enhancement is knowledge enhancement, aiming to augment RIs on the feature level. The core idea here is to leverage LLM's extensive word knowledge and powerful reasoning abilities to explicitly enrich the features of users or items. In this category, LLM ERIs often utilize explicit knowledge to augment the recommender system. On the left, we have summary text augmentation. Here, the LLM is prompted with existing users or item textual interactions. For example, given a user who has viewed something he or she is interested in, the LLM then generates a summary text like he or she likes something, which captures the user's preferences or item's characteristics. This summary text is then often encoded by a general language model such as BERT and used as an extra feature for the RS model. On the right, we have knowledge graph augmentation. Instead of unstructured text, LMs can be used to generate a knowledge graph or augment an existing KG for enhancing traditional RS. An LM can be prompted with an item's name to ask, given an item named something, does it have the attribute something? And the LM then helps to build or complete a knowledge graph. This structured knowledge encoded by a knowledge graph encoder also serve as some supplementary features of the recommended system. Both methods aim to supplement reasoning and understanding knowledge for features, directly address limitation 1. Since these enhanced features can be derived and saved in advance, the demand for IRM will be avoided during the service, leading to efficient inference. Our second category, interaction enhancement, is designed to tackle the critical issue of data sparsity in traditional recommender systems. The idea is straightforward. Use LLMs to generate new synthetic user-item interactions, effectively augmenting the training data. This augmentation only occurs during training, so it introduces no additional inference burden during service. As illustrated in the diagram, we categorize these approaches based on the type of output the LM provides, text-based and score-based. On the left, we have text-based interaction enhancement. Here, the LM is prompted to directly augment by recommending an item name, like item 2. For instance, given a user who has viewed something and a candidate site, item 1, item 2. The LM might be asked to choose from them. The generated item name is then added to the dataset as an augmented interaction. On the right, we explore score-based interaction enhancement. To mitigate the out-of-corpus problem and the difficulty of selecting from a large item set, these methods leverage the LM to derive the losses or probabilities of possible interactions for a set of candidate items. As shown, the LM outputs scores of 0.02, 0.31, 0.05 for different items, and augmented items are generated by ranking. Both text-based and score-based methods serve the same purpose, to enrich the interaction data for training, making the recommender systems more robust, especially in sparse data environments. Our final major category is model enhancement. This line of work directly injects the powerful abilities and semantics of IMs into traditional recommender models. The goal here is to address challenge 3, where traditional models often overlook semantic understanding. This slide illustrates the first and second key subcategories of model enhancement. On the left, we have model initialization. This approach leverages LMs to pre-train or initialize the weights of the RS model before the main training process. Just as pre-trained weights can help model convergence and preserve learned information in other fields, LMs can inject rich semantic knowledge to the RS model's parameters. Some approaches apply pre-trained weights to the whole RS model, while others are for the embedding layer. On the right, we explore model distillation. This technique, inspired by knowledge distillation, involves transferring the knowledge from a large, powerful LM, that is the teacher, to a smaller, more efficient RS model, that is the student. Despite the gap between discriminative RS models and the generative LLM, existing studies design feature-based and response-based distillation ways to address such an issue. Both model initialization and model distillation only need the LLM to assist in training RS models, ensuring that LLM usage is eliminated during the serving, thus meeting the latency requirements of real-time service. Continuing with model enhancement, this slide presents the third and fourth subcategories. On the left, we have embedding utilization. In this approach, embeddings derived from LLM, such as the hidden states of the last transformer layer of the LLM, are directly utilized to enhance traditional RS as a semantic supplement. The diagram shows the LLM outputting embeddings which are then fed into RS model. This line of work can be categorized into user-only, item-only, and user and item based on the aspects LLM embeddings addressed in the traditional RS. On the right, we delve into embedding guidance. This approach differs from direct embedding utilization as it uses the LLM embeddings only as the guidance of training or parameter synthesis. The diagram shows that LLM embeddings influencing the RS model through a guidance loss, denoted as LGuide. This is particularly useful for user-only or user and item scenarios. These methods collectively demonstrate the versatility of LLMs in enhancing different aspects of the recommendation model, moving beyond just data level improvements. All these techniques are crucial for building efficient and powerful LLM enhancement recommender systems that can truly understand and fulfill user needs. Okay, next, let's welcome Mr. Peng Yuejia for the section 2.
Okay, and let me share my screen. Okay. Hi everyone. I'm Peng Yuejia from City University of Hong Kong, and I will give the introduction of the knowledge enhancement part. So let me start by introducing the concept of knowledge enhancement in LLM enhanced recommender systems. So traditional recommender systems mostly rely on user item interaction data. However, they often lack external knowledge that is essential for reasoning and understanding user preferences. And LLMs can fill this gap by injecting word knowledge and reasoning capabilities into the RS pipeline. And as shown in the figure, the LLM can like generating some textual summaries such as he or she likes something based on the user browsing history. And these summaries are then encoded via a text encoder and fed into the RS model. On the item side, the LLM can also answer structured prompts like does an item have a certain attribute? And supporting knowledge graph construction and enrichment. And this structure, the information is encoded through a KG encoder. And based on the form of knowledge used, we categorize the enhancement into three types that are summary text, knowledge graph, and their combination. And this categorization allows us to systematically understand how different kinds of external knowledge can be utilized to improve recommendation qualities and explainability. And we first focus on the summary text subcategory of knowledge enhancement. And the idea here is to leverage LLMs to generate natural language summaries that describe either user preferences or item characteristics. And these summaries serve as additional semantic features for traditional recommender systems, improving both the reasoning and personalization. And the LLM returns a concise, the textual summary, such as he or she likes the romantic comedies. This output encodes rich semantic information that would be difficult to infer from like interaction data alone. And the generated text is then passed through a text encoder to convert it into dense representations, which are compatible with the recommendation model's input space. And this strategy allows us to enrich traditional RS models without modifying their architecture or relying on fine-tuning the LLM. And we further categorize summary, the text enhancement, into three types based on what is summarized. The first one is user only, such as inferring multifaceted preferences from browsing behavior. The second is item only, such as generating detailed product or category descriptions. And the third one is the user and item. It's the combination. And the first paper is lame. So the background here, the explainability of recommendation system is crucial for enhancing user trust and satisfaction. Motivation is the fine-tuning LLM models for recommendation tasks incurs high computational costs and alignment issues with existing systems, limiting the application potential of proven or proprietary or closed the source LLM, such as GPT-4. The key components are semantic embedding, the user multi-preference extraction using the zero-shot prompting, and semantic alignment. So first is about semantic embedding. In this step, authors use a text encoder to transform all items titles and user behavior sequences into semantic factors, rather than using just the simple ID embeddings. And this semantic representation enables downstream modules and LLMs to better utilize natural language understanding, where here the M is the embedding matrix of all item titles. The second is integrated model module. Then can plug into mainstream sequential recommenders like susrec or bird4rec, but replaces their ID-based embeddings with semantic text factors and preserving the model structure and ensuring better interpretability. And in this step, authors adapt a standard sequential recommender to use the semantic embeddings. For user, their history factors are combined with precisional encodings to form the model input EU, and which then produces sequences features QU. And by using meaningful semantic inputs, authors make the downstream reasoning and explanations more in the interpretable while keeping the original recommender structure. And for extracting multi-preferences using LLM zero-shot prompting, here the authors use a zero-shot prompt with the LLM to summarize the user's multiple preferences from their history. The LLM generates a list of textual preferences, which are then encoded as semantic vector, PU. And this approach leverages the LLM's understanding without any model tuning, providing diverse and user-specific features for later alignment. For the next module, the semantic alignment via multi-head attention, this module uses multi-head attention to align the user's sequence feature, that's the QU, with the LLM-generated preference vector, the PU. The formulas show the attention and feed-forward steps with normalizations and residues to stabilize learning. The result is a user representation that both effective for ranking and interpretable through the extracted preferences. For the prediction, for each time step T, authors take the user's aligned feature vector, that's the FUT, and the embedding of candidate item MI, and compute the inner product. This operation measures the semantic similarity between the user's current preferences and each possible item in the shared semantic space defined by the text encoder. And this slide shows the lane improves the NDCG at 10 and hit rate at 10 across all datasets and base models. And the key takeaway is the lane enables plug-and-play integration of powerful LLMs for explainable recommendation in real-world systems, providing enhanced performance and user-friendly explanations without any need for LLM fine-tuning. And next, we introduce the item-only method, GPT Aug News. The background here is the explainability and informativeness of news metadata, especially the category information, play a crucial role in personalized news recommendation. And the motivation is the manually creating detailed descriptions for news categories is labor intensive, and existing category templates are too generic and provide insufficient semantic guidance. Pre-trained language models often fail to interpret short category names effectively without richer context. So the contribution is generating descriptions with LLMs and incorporating descriptions into recommendation models. And to enrich the semantic meaning of categories, the authors use GPT-4 to automatically generate the descriptions. The prompt is simple and fixed, and it returns clear text about what a category typically includes. These descriptions are longer and more informative than short category labels, and they require no additional tuning. After generating the category description, the next step is to feed it into the model. The title and the description are concatenated using the SEP token, just like standard BERT, the input formats. And this augmented input is then encoded and used in the downstream recommendation models, improving the system's understanding of both the topic and the context. As we can see in the table, this method consistently outperforms both the title-only and title plus template-based the baselines across all the tested models. And this highlights the very important takeaway. So LLM generated category descriptions over a simple and generalizable and training-free way to enhance item size the representations, which can be applied across architectures without additional domain-specific tuning. And this makes GPT-Org News both effective and highly practical for real-world deployment. And for the user and item combination, we introduce KR. KR is designed to break the boundary of closed word recommenders by introducing external knowledge from larger language models. Existing recommender systems work only on in-domain behavior data, meaning the valuable common sense or reasoning capabilities. However, using LLMs directly as recommenders is neither accurate nor efficient. So KR solves this by extracting two kinds of knowledge, the reasoning about user preferences and the factual item information, and encoding them into compact factors that classical recommenders can use directly. And it is model agnostic, explainable, and supports fast inference. The first stage named the knowledge reasoning and generation. This stage is responsible for acquiring open world knowledge from LLMs. And since LLMs struggle with complex composite tasks, and here they use the factorization prompting to break down reasoning into specific factors, like the theme or director. And two prompts are designed, one for analyzing the user's historical behavior and preferences, and another for generating descriptive knowledge about the candidate items. The outputs are plain text summaries, KIP and KIL, which will later be encoded. These prompts guide LLMs to produce consistent and rich information aligned with recommendation needs. And after we get the raw text outputs from LLMs, we need to convert them into a form usable for CTR models. And this is done by two steps. First, a knowledge encoder converts each piece of the textual knowledge into a dense factor via average pooling or CLS token. And second, a hybrid expert adapter transforms these factors into the recommendation space. It uses a mixture of expert structure with shared and dedicated experts to capture both the general and specific semantics. The final user and item knowledge factors are then added as new input fields into the CTR model. And during training, these components are optimized jointly with the backbone, enabling the model to combine open world knowledge with traditional interaction signals. This table shows the improvement brought by KR across 9 standard CTR the models, whether the base model is DeepFM, AutoInt, or DRN. The addition of reasoning and factual factors leads to consistent and statistically significant gains. Importantly, this is achieved without redesigning the model structure. The open world knowledge is pre-computed and stored, so inference time remains fast. And overall, KAR provide for rooms and recommender systems in a scalable and effective way. And another work is Sling. Sequential recommendations captures users' dynamic interests, but traditional models rely on limited user item interactions and struggle with exposure bias. Large language models offer strong reasoning ability and open world knowledge, yet applying them directly is costly and often produces irrelevant results with one-step prompting. To tackle these issues, this paper proposes SLIM. It's a step-by-step knowledge distillation framework, and it uses train of thought prompting on a large teacher model to generate recommendation rationales, which are then distilled into a small student model like Llama 2 7B. So Slim enables the student model to reason step by step with only 4% of the teacher's size. It supports both ID-based and ID agnostic recommendation and performs competitively with much lower cost. This slide describes how the Slim framework uses a large teacher LM to perform step-by-step recommendation reasoning using train of thoughts, the prompts. The teacher model outputs a rationale consisting of a user's preferences, preferred brands or categories, and recommended items. These rationales are then used to fine-tune a much smaller student model. The authors adopt a simplified prompting template, TS, and apply standard language modeling laws, as shown in the equation, and to supervise the student model. And the student after training can generate similar reasoning steps, enabling lightweight deployment. So this slide presents how Slim applies the reasoning knowledge from the student model to the recommendation process. The student generates natural language rationales, RU, which will be encoded using a text encoder like BERT in the first equation. And here FI is the item's description, such as title, brand, or category. This yields a user side and item side embedding in the same semantic space. Authors then introduce two application settings. The first is ID-based recommendation. The authors combine these text embeddings with traditional ID embeddings through a fusion mechanism as shown in the equation. And GL function aligns dimensions, yes, dimensions via linear projection, and GF function is a fusion layer. This lets the model integrate both the open world knowledge and collaborative signals. The second is ID agnostic, the recommendation. In scenarios like cold start, we can just skip the ID embeddings entirely and use only the text-based reasoning as shown in the third equation. And GT function is the transformation layer that projects both sides into a shared space for similarity matching. The experimental results in table demonstrate that Slim achieves state-of-the-art performance across different the background models and datasets. For the takeaway, Slim enables small language models to act as effective reasoners in sequential recommendation by distilling step-by-step rationales from LLMs at a fraction of the computational cost. And this slide focuses on the second category of knowledge enhancement. That's the knowledge graph, or we can name it as KG. While summary text provides unstructured descriptions, structured knowledge graphs offer a more systematic and integrable way to represent relationships among entities. This structure is often easier to incorporate into recommender systems, especially when we need consistency and interpretability across users and items. The idea here is to utilize LLMs to either generate new knowledge graphs or augment the existing ones. For example, given a prompt like, does this item have a particular attribute? The LLM can infer and output new facts or relationships that are not explicitly available in the dataset. And these outputs are structured into graphs, which are then coded using a KG encoder and integrated into the recommendation pipeline. This allow us to incorporate high-order semantic relationships into the user or item embeddings. And here we divide the existing work in this direction into two categories. The first is generation, where the LLM is used to construct a new entity relation, the triples or reasoning paths from scratch. And completion or fusion, where the LLM fills in missing links or refines existing KGs to improve their usefulness in recommendation. In practice, this structured approach helps the RS model go beyond direct interaction signals and leveraging further relationships. And first, let's take a look at the generation. The work which introduced here is LMRG. Sequential recommendation aims to predict the user's next interaction by modeling historical behaviors. Traditional methods, including those enhanced with knowledge graphs, often rely on static structures and cannot generalize to unseen patterns or diverse reasoning paths. And these slides introduce um, the yeah, and this slide introduces LMRG. So it's a novel framework that leverages large language models to build personalized reasoning graphs on the fly. Instead of relying on explicit external knowledge, LMRG generates multi-hop reasoning chains using only user interactions and attribute information. The core idea is to let an LLM act as a dynamic reasoning engine. It first builds candidate reasoning chains, then verifies and scores them using a self-checking process, and finally expands them to improve coverage and robustness. LLMRG consists of three modules: the trained graph reasoning, and self-verification and scoring, and the divergent extension. These modules work together to generate and refine user intent specific reasoning chains, and the model fuses this with a base sequential recommender to yield the final prediction. And author begin with the trained graph reasoning module. For each user that the LLM constructs multiple candidate trains or see the I based on their sequence SU and attribute AU, optionally referencing a knowledge store. To verify reasoning quality, the trains are randomly perturbed, masking certain items or attributes. And the LLM performs abductive reasoning, like can it still explain the interaction despite these missing parts? And each train is then scored via learned function. And only trains with high scores are retained for further use. This state ensures the interpretability and robustness before fusion with the base model. And after verifying the reasoning trains, the authors move to the divergent extension. It's the next step. The LLM requires the graph for unexplored nodes, creating new trains that enhance diversities and completeness. If these new trains contracted previous knowledge, um, and the knowledge base is then be updated, making the system self-improving. And finally, embeddings from the base model. That's the E base, original reasoning, E ORI, and divergent reasoning, E diff, are fused by this equation. This factor is passed to an MLP for next item prediction. This fusion integrates explicit reasoning paths with traditional sequential patterns. LLMRG outperforms all the baselines across multiple datasets. For example, on the movie lens 1 million using GPT-4, we see a 28% gain in NDCG at 10. Unlike previous models that rely on pre-built graphs, LLMRG adaptively builds and verifies reasoning trains from scratch. It supports the dynamic, user-specific reasoning and can even expand its own knowledge. The takeaway, the takeaway is clear. LLMRG makes it possible to inject rich, interpretable reasoning into recommender systems and powered entirely by LLMs without needing external the knowledge bases. And in recent years, knowledge graphs have been widely used to enhance recommender systems by capturing structured information among users, items, and entities. However, these methods face three critical limitations. First, many KGs are incomplete, with missing or sparse relationships. Second, they typically convert textual entities into IDs, losing the underlying semantic meaning. Third, most models rely on multi-layered GNNs, which suffer from noise accumulation and oversmoothing, especially for high-order relationships. And motivated by the strong semantic reasoning abilities of LLMs, this paper introduced the Collar KG, a novel approach that leverages LLMs to understand and complete KG information. So Collar KG converts item and user-centered subgraphs into textual prompts, which are interpreted by LLMs to generate semantic embeddings. These embeddings are used to construct a semantic item-item graph and are integrated into traditional recommenders using alignment and augmentation modules. This page explains how Color KG enables LLMs to comprehend structured KG data. Since LLMs cannot directly interpret the graphs, the model extracts the subgraph centered around each item. And these item-centered subgraphs include both first-order neighbors and randomly sampled second-order connections. And next, these triples are transformed into textual form. The first-order set is encoded as the flat list DV, and the second-order relations are described using natural language DV, that's the prim. Combined with the task-specific instruction prompt, and the full input is passed to an LLM. The LLM processes this textual input and outputs natural language comprehension, summarizing and reasoning about the item's context. And a frozen sentence embedding model, that's the P, is then used to convert this text into a dense vector, SV, which serves as a semantic embedding of the item. This process allows Color KG to retain semantic meaning and mitigate knowledge sparsity by leveraging the LLM's reasoning capacity. And this page focuses on how Color KG leverages semantic embeddings to model high-order relationships and integrate them with traditional user-item interaction models. So once semantic embeddings are obtained for each item, Color KG constructs a semantic item-to-item graph. For any two items, say Vi and Vj, their edge is weighted by cosine similarity. And for each item, the top k most similar items from its semantic neighborhood. That's the NKVI. And to integrate semantic and collaborative information, Color KG uses adapter layers to project semantic embedding SV and SU into the same space as ID embeddings. The fused representation, HV and HU, are then created by averaging. Additionally, to further enrich the item representation, the model aggregates information from semantically related items. Attention weights are computed based on the embedding similarity and used weight neighbor contributions. The final augmented representation captures both the direct and semantic neighborhood information, leading to stronger and more informative embeddings for downstream recommendation. And the experimental results as shown in the table clearly validate the effectiveness of Color KG. And the main takeaway of this work is that it successfully unifies structured graph knowledge and unstructured semantic information using large language models. And this slide introduces the combination strategy, which integrates both summary text and knowledge graph representations for recommendation. While summary text provides rich unstructured insights and knowledge graph over structured relationships, each has its own strengths and limitations. Some recent works propose to combine both sources, aiming to capture complementary information. So for combination, we introduced one paper as called the RAC, SKAR RAC. Educational recommendation and knowledge tracing tasks require deep understanding of what learners know and how concepts are related. And traditional approaches often model concepts as discrete IDs, and which leads to poor generalization, especially when encountering rare or unseen concepts. And these methods ignore both the semantic content of the concepts and their structural relationships within a knowledge graph. To address this, the authors propose SKAR-RAC, a structure and knowledge-aware recommendation framework. SKAR-RAC integrates large language models, structured concept graphs, and contrastive learning to build richer and more generalizable representations. This page presents how SKAR-RAC uses language models to interpret educational concepts semantically and structurally. Each concept, such as table, is associated with a textual definition and linked to its neighbors in a concept graph. These components are combined into a structured prompt and passed to a large language model. The prompt includes the base concept, its predecessors, successors, and contextual instruction. The LLM processes this prompt and generates a coherent and enriched the textual explanation of the concept. This LLM-generated interpretation captures both the linguistic semantics and structural dependencies among concepts. It serves as a more expressive representation than traditional one-hot or ID-based encodings, enabling the downstream models to understand the ambitious or sparse concepts more effectively. And once SKAR-RAC generates concept interpretations, it encodes them using a transformer encoder to obtain dense semantic embeddings. These embeddings are then aligned through a graph-based contrastive learning objective. A concept graph, that's the G, is constructed based on the prerequisite relationships between concepts. For each concept, authors define positive peers as its direct neighbors and negative peers as non-neighbors. The model is trained to bring embeddings of positive peers closer while pushing negative peers apart, thus encoding both the semantic and the structural signals. The resulting embeddings are used in two downstream tasks. First, a transformer-based recommendation model processes sequences of concept embeddings and predicts the next concept or answer. And second, for knowledge tracing, the model estimates the learner's mastery of each concept using the enriched embeddings. This dual application demonstrates the generalizability of SKAR-RAC's representations across both recommendation and knowledge modeling. And the results in table clearly show the SKAR-RAC sets a new state of the art on three widely used educational datasets. And in summary, SKRREC demonstrates that incorporating both knowledge structure and semantics is essential for building effective educational recommendation and knowledge tracing systems. And here we give a summary of knowledge enhancement section. For summary text, this work uses LLMs to generate natural language summaries that describe either user preferences or item characteristics. These summaries serve as additional semantic features for traditional recommender systems, improving both reasoning and personalization. For a knowledge graph, the idea here is to utilize LLMs to either generate new knowledge graphs or augment existing ones. For combination, which integrates both the summary text and knowledge graph representations for recommendation, while summary text provides rich unstructured insights and knowledge graphs over structured relationships. Each has its own strengths and limitations, so combine both sources can capture complementary information. And next part will be introduced by Ziwei. Welcome.
Okay, let me share my screen. Oh, hold on. Okay, let's go. So, hello everyone. In this section, we'll present the details about LLM in enhancing user-item interactions. So, we will divide the category in two aspects. The text-based aspects, as shown in Figure A. The text-based methods first conclude the candidate set and then utilize LLM to conduct a possible next interactive item to achieve argumentation. And for the score-based one, we can see it in Figure B. The score-based methods utilize LLM to rank the importance of each item, and after that, they leverage its ranking score to do the argumentation. So in these sections, we'll present several insightful papers that leverage the power of LLM as user-item interaction enhancement in the recommendation task. We will first introduce four awesome text-based works and then present three awesome score-based works. And for the first one, we present LLM RAG. And this work recognizes the limitation of regarding LLM as a data augmenter and summarizes them as two problems. The first one is incomplete input information, which means it's hard to enable LLMs to reason over full user interactions patterns due to the limited input token. And the other one is the low quality of the generated data. It points out that LLM generators often introduce low quality content that may compromise the results because of the noise and the hallucination. So specifically, to address the first problem, they also designed two individual modules from a natural language perspective. For the implicit feedback augmenter, since LLM's limited length of input token often induce the incomplete interaction information, they also first construct an item candidate pool by leveraging a basic recommendation model, and then randomly select the historical interaction item with the side information to feed them into LLM for data generation. And moreover, the authors also leverage one more user profiling and item attribute enhancing modules to summarize user interactions and unify the item attributes, further relating the problem of limited input token. And for problem 2, they also propose another two modules. In the first one, they also leverage the extending sort mechanism with the BPR loss to filter the values and select the top score for noise pruning, like this. And for the other one, they also first randomly map the features of selected subset of the node and replace them with the LM-generated feature vectors. And after that, they leverage the feature restoration laws to compare the mask matrix with the original one to further enhance augmented semantic features. And experimental results shows that LM RAG achieves optimal performance with significant improvement compared to powerful self-supervised methods and data augmentation methods, showing its effectiveness and generality. For the second paper, we will introduce LlamaRag. This paper identified the shortcomings of conventional methods known as data sparsity and long tail problem, and also the shortcomings of LLM-based methods known as collaborative information loss. So the author raised three research questions. Question one, how to leverage LLM's reasoning ability in conventional methods, and how to introduce collaborative information in LLM-based methods. And third one is how to aggregate these two kinds of methods properly. So here's an overview of the framework, which allows the conventional and LLM-based implementations to mutually augment each other and adaptively aggregate results for different kinds of recommendations. So then we will detail how Lamarck answered the mentioned research questions. For the first one, they also proposed the data augmentation. For the direct recommendation task, they prompt the LM to rank each item pairs based on the user's likely preference and rewrite the corresponding BPR laws like this. And for the sequential recommendation, they leverage LM to predict the user preferred items in the uninteracted list and then inserting them in the interaction sequence. And when it comes to the rating prediction task, the LM is prompted to do in-context learning to provide side information of item features. So to answer the second research questions, they also designed two prompt augmentation strategies. And the first one utilized the information from similar users. Specifically, it leveraged cosine similarity to recognize similar users and regarding the interactive items of these users as collaborative information to enrich the prompt for LM instruction tuning. And the second one is quite simple. They just combine the prediction results from the conventional methods within the prompt to augment the instructions. And lastly, to answer question 3, Lamarck introduced the adaptive aggregation to aggregate the outputs of different models. And by leveraging this predefined long tail coincidence, which quantify where the user is located in the tail of the distributions. It can calculate the utility score for no matter rating prediction task or the top gate recommendation task to adaptively aggregate the advantage of conventional methods and LM-based methods. And the experiment results present that Lamarck shows optimal performance no matter backbone is direct recommendation models or sequential recommendation models or rating prediction models, validating the effectiveness of the design framework. And for the next article, we present LMHD. And this paper identifies the challenges that hinder direct application of LM in denoising recommendation and conclude them as three challenges. The first one presents the high cost of LM summarizations when processing the preference of all users across all domains. And the second one points out the misidentifying of hard samples and noise samples. As shown in the left figure, hard samples and noise samples tend to present similar patterns in both prediction scores and loss values. However, conventional methods are struggling to distinguish the difference, leading to the suboptimal performance. And the third one is a biased user preference summarizations, which means the presence of false positive items in the historical interactions can lead to the biased user preference summarizations. So here's an overview of the framework. And next, we will detail the role of different modules and clarify how they solve the corresponding challenges. For challenge 1, high cost of LM summarizations. LMHD introduced a variance-based sample learning. Following the observation of previous work, harder samples present relatively higher prediction score variance compared to the noise samples. LMHD calculate and sort the prediction score of the positive and negative items as follows. So the hard samples can be defined as this, which can provide to feed all the identified noise samples to the LMs for scoring, significantly reduce the computation cost of LM. And for the challenge 2, LMHD introduced a novel sample scoring mechanism. Specifically, they also designed two paradigms, the pairwise and the pointwise. For the pairwise sampling, they set different thresholds to control the hardness of samples and to avoid the problem that harder samples at the early training stage might hurt the generality. They also smoothly changing each threshold during each training iterations. And moreover, considering the user's preference for the positive items does not significantly surpass the negative one, the authors also propose a pointwise sample scoring. It utilizes the indicator functions to calculate the difference of two thresholds and then doing the selection procedure like this. And lastly, to adjust the change 3, LMHD introduced the iteratively preference updating modules to alleviate the side effects that false positive and false negative item brings and generate the effective user profiles. Specifically, they also refine user preference iteratively by excluding dislike and incorporating likes, and then processing the variance scores of each user item pair in positive and negative items to select the competent items. And at last, leveraging this ranking score, LMHD can refine the original preference based on identify false positive and false negative to construct unbiased user profiles. So in the comprehensive experiment, LMHD shows remarkable recommendation ability under four different recommendation backbone in three public datasets evaluated by four metrics, validating the effectiveness of design structures. And for the last work under the text-based category, we present sample LM. In this work, they also find the difficulty in applying LM to tabular data synthesis and conclude them as two severe problems. Problem 1, inconsistent distribution and diversity. As shown in the left figure, these challenges arise from the distribution mismatch between LM's inherent knowledge and target datasets, leading to a reduced output diversity. And the second problem is the distribution difference caused by LM. And this is because of the inherent difference caused by LM's input and output processing, which result in the distribution gap and differentiated feature interaction frequency between the generated and the original data. So the figure below is the overview of the whole framework. And next, we will detail the role of different modules and different stages to clarify how they solve the corresponding problems. To adjust P1, the design instruction and sample examples from the original datasets are selected to serve as the input for the LM, producing the initial synthetic tabular data. And specifically, it begins with the sample selections by leveraging k-means method, which can ensure that each group of examples contains samples from diverse regions of the original dataset distributions. The whole approach can then be formalized as the equations present below. And to adjust the P2, sample LM performs attribute-based importance sampling operations. Since its challenges to assume that each feature field is independent and impractical, they propose a new semi-independence assumptions, which means feature fields containing significant interactions are non-independent, while others, not that important items, are independent to satisfy the situations. However, it is still challenging to identify the significance of interactions, so they design the feature interaction extraction. Specifically, they quantify the importance of each feature to the output by calculating the model performance degradations after ablating this feature with the first-order tail expansions. And then they extend the first-order tail expansions to the second order to calculate the importance of feature I to the importance of feature j. So therefore, the sum of absolute value of interactions can highlight the significant features interactions in the whole dataset and can be used for further refinement. And then, since each tabular samples contain not only a set of features but also label, they also designed to train a task-specific model to acquire the labels. And at last, leveraging these well-trained discrimination models and the acquired feature groups, the importance weights of samples can then be formalized as below. And the experiment results shows that sample LM achieves remarkable results on 5 public datasets, validating the effectiveness. And they also first test the utility of synthetic data by comparing the prediction performance of different methods after injecting synthetic data into the original data. And moreover, they also validate the utility by supplanting the real data with synthetic data in training a predictive model. And next, we will introduce 3 remarkable work under the score-based category. For the first one, we present LM-ins. This work identifies the limitation of current methods as 2 challenges. Challenge 1 is the distribution gap, which means the generated embedding are created from the content feature, while the behavior embeddings are changed from the user item interactions, leading to the distribution gap and the performance gap between the code items and warm items. And challenge 2 is the LM's inadaptability, which means directly applying LM to interaction generations need to be further aligned and unified. So here's an overview of the LM-ins framework. The LM simulator is designed for generating possible user set for the code items. And the hierarchical interaction simulator is the main procedure that designed for mimicking potential user interactions for each code items and transfer them to the warm items. And the embedding updating is designed for adaptively merging the interaction of code items and warm items. And we will then detail the procedure of hierarchical interaction simulator, which is the main procedure. Okay, for this modules, it contains 2 parts. the embedding-based filtering, and the prompt-based refining. For the embedding-based filtering, it processes information of both the semantic and collaborative sides. To process the semantic information, they also construct a llama subtower to obtain the user and item representations and leverage the BCE laws below to chain the structures. And to process the collaborative informations, they also construct analysis collaborative subtower. Specifically, it contains three kinds of laws to leverage the collaborative information. The main BPR loss is to narrow the gap between the embedding of code items and the virtual embedding of warm items. And the DIS loss is proposed to enhance the consistency between the corresponding embedding on the collaborative side and non-collaborative side, while the IDE loss is to achieve consistency on the embedding distance side. And leveraging these three laws, the model can enable the side information without collaborative information to learn the related features. And after obtaining the user item embedding from Llama subtower and collaborative tower, LM-ins leverage the prompt-based refining to further refine the generated interactions. It first concave the two embedding together to get the overall representations and utilize the inner product to avoid them interfere each other. And then utilizing a well construct instructions to prompt LM to filter the low quality interactions. And experimental results shows that LM-ins achieves optimal performance under different backbones and present remarkable performance in comparison with other LM-based recommendation models. And next, we will introduce another score-based interaction enhancement methods, LM for DSR. And this work also aims at denoising sequential recommendation task and identify two severe challenges when directly applying LM to denoising SRS. And challenge one is the inability of LM, which means direct application of between LMs may not be competent for the denoising task. And the left figure shows that an example where LMs typically misidentify all items in the sequence as noise. And the challenge two is the hallucination of LMs. It means that the reliability of LM's output remains questionable because of the complexity of the task and the hallucination of LMs. So here's an overview of the LM for DSR, featuring a self-supervised fine-tuning method and an uncertainty estimation mechanism to fully explore the capability of LMs. Specifically, to adjust C1, LM for DSR construct a new dataset and leverage the supervised fine-tuning to empower LMs with denoising ability by using a find and replace task. By prompting the LM use left instruction examples, they also construct a new binary prediction dataset and formulate the training operative as follows. But however, there's still one limitation that current LM-based denoiser can only adjust a single noise item per sequence. So they also propose another limitation, which is called the inability for multi-noise scenario. And to adjust the inability for multi-node scenario and the hallucination of LMs, the uncertainty estimation model is introduced to gauge a model's confidence in its response. And regarding the LM's provided probability of text noise items as LM's confidence in identifying the noise, the problem can be simplified as follows to obtain the probability values of all noise items in the sequence. And moreover, the experimental results also shows that the reliability of probability provided by the LMs. And for the experimental results, LM for DSR achieves optimal results on three raw public datasets, validating the effectiveness of proposed methods in the real scenarios. And moreover, to highlight the denoising ability of LM for DSR, they also conduct experiment on the same three public datasets while randomly adding some extra noise. And from the result table, it is notable to see that LM for DSR maintain the performance, while other methods show a significant decrease. And for the last paper under the score-based interaction enhancement, we introduce EIMF. And this work identifies the problem when leveraging the semantic information to model user behavior information and categorize them as two problems. Problem one, demand conflict, and which means traditional SR has high real-time requirements, while the fine-tuning and inference of LMs requires a lot of time and computing resources, leading to the demand conflict. And problem two is the misunderstanding of the user's real interest. And this means the semantic information from user item content has significant gap between with the behavior information from weight chain recommendation model. So here's an overview of the framework of EIMF, featuring implicit behavior interest modules, explicit semantic interest modules, and the joint learning modules. And next, we'll detail the role of different components and clarify the methods behind the motivations. And to adjust the P1, EMF introduced like explicit behavior interest to fully explore LM's capability while reducing the inference cost. For the first step, EMF divide the users into groups and utilize LM as summarizers to reduce the inference cost. And then for the interest embedding, EMF requires the semantic interest embedding by utilizing the target item as a key, and which can be used for further alignment and semantic predictions. And to adjust the P2, EMF then combines the implicit behavior interest modules with the explicit semantic interest modules by joint learning three kinds of tasks. And firstly, EMF obtains the implicit behavior interest by SR models, and then using similar target well attention network to acquire the behavior embedding to construct the laws. And then for the joint learning procedure, they design three kinds of tasks. The first one, they introduce the semantic prediction task, which calculate the score between user semantic interest and item task as follows. And for another model alignment task, EMF builds the constructive laws to align the semantic embedding and behavior embedding as this. And after that, EMF constructs the main recommendation task, which multiplies the user behavior interest representations and the item representations to calculate the probability and construct the following rec loss. And finally, the whole loss can be formulated as the weighted sum of the three losses mentioned before. The experimental results shows that EMF achieves remarkable results on the three public datasets. And moreover, the experiment for performing on different backbones shows a significant improvement, further evaluating the effectiveness of proposed methods. And so here we give a conclusion of our work on interaction enhancement for LLM enhanced sequential recommendations. And the text-based methods and this kind of methods leverage LLMs to give out the names of procedural interactive items in the user item interactions as the argumentations. The score-based methods, they use the LLMs to derive the logics of possible interactions and generate the augmented items by ranking. And next is the coffee break.
Okay, all right, guys, let's start the second half.
Okay, is my voice okay?
Yeah, all good.
Thank you. Hello, everyone. I'm Mao Ling. And let me now turn to the concept of model enhancement in large language model enhanced recommendation system. Beyond simply providing external knowledges, large language models possess powerful semantic capabilities that can be directly integrated into traditional recommendation models for comprehensive model enhancement. Traditional recommendation system models are generally composed to two main components: the embedding layer, which captures the relations between items, and the hidden layers, which extract more complex user preferences. Large models can enhance both of these architecture components through different integration strategies. As you can see in this figure, we can categorize the model enhancement into four main approaches. The first is model initialization, the second is model distillation, and the embedding utilization, and the embedding guidance. The first two categories, model initialization and model distillation, improving involving applying large model capabilities to enhance the entire recommendation system's architecture. In contrast, the embedding utilization and embedding guidance focus more specifically on leveraging large model semantics to improve the embedding layer. An important practical advantage is that the model initialization, model distillation, embedding guidance only require large model assistance during the training phase, which will eliminate the large model overhead during the serving. Additionally, embedding utilization can pre-catch large model embedding before inference. This design ensures that all these enhancement approaches can meet the strict latency requirements of full-time recommendation services, which will still benefit from large language capabilities. Let me turn to the subcategory. We first focus on the model initialization of the model enhancement part. The idea of the model initialization here is to leverage large language the large model pre-trained ways to initialize the recommendation model parameters before training begins. This transfers the rich semantic knowledge from large model pre-trained directly into the recommendation system model architecture, providing a strong foundation for the recommendation system tasks. Instead of random initialization, we use the corresponding weights from pre-trained large models that have already captured the semantic relations. This accelerates model coverage and preserves the semantic knowledge that influences how the model learns the recommendation patterns. The pre-trained weights are transferred through parameter mapping techniques, ensuring the compatibility between large language models and recommendation architectures. This enhances traditional models without requiring complex modifications or expensive fine-tuning during the deployment. We here categorize the model initialization into two types based on the transfer scope. The whole type, where the pre-trained weights initialize the entire recommendation model architecture, transferring the comprehensive semantic knowledge across all layers, and the embedding where the initialization focuses on the embedding layer, preserve semantic present representations while allowing other layers to learn recommendation-specific patterns. Let me first introduce the whole subcategory, one work of the whole subcategory, the CTRL. The background of CTRL is that the CTR prediction is a core task in recommendation system, while a traditional collaborative model can capture user preferences through feature concurrence. And the motivation of this work is twofold. The first is that one, how the encoding could discharge semantic relations, leading to poor performance in code start scenarios. And the second is that the direct use of pre-trained large language models is computationally expensive and fails to meet low latency requirements for the online inference. There are two key stages of this CTRL. The first is cross-modality knowledge alignment, and the second is supervised fine-tuning. The CTRL proposes such a two-stage framework, and the first stage, cross-modal knowledge alignment, is that we can feed the tabular data to a collaborative model and the same data as text prompts to the large language model. The contrastive learning aligns their representations, essentially teaching the collaborative model to understand the semantics without becoming a language model itself. And then we can fine-tune the now semantically aware collaborative model on the CTR tasks. Crucially, only this lightweight model goes online. The large language models stays offline. We can get the semantic understanding during training, but keep fast inference. And here is the experimental results of the CTRL. This table shows that the CTRL consistently outperforms the state-of-the-art model across multiple data sets, including the Mullins, Amazon, and Alibaba. For example, CTRL achieves these significant AUC improvements while maintaining comparable inference efficiency to traditional collaborative models. The key takeaway is that the CTRL enables practical integration of semantic knowledge from the large language models into the collaborative CTR models, delivering the superior performance with this industrial grade efficiency through its two-stage training paradigm that separates knowledge and alignment from the online inference. The another work of the whole subcategory is the flip. The background is quite the same. The CTR prediction is a cost task in the recommendation system, while the traditional ID-based models use only one-hot encoding, and the pre-trained the large language models use the textual modality. And the motivation is also the twofold. The first is that the one-hot encoding discharges semantic information, leading to the poor performance in sparse scenarios. And the second is that the large language models struggle with the field-wide collaborative signals and have high computational costs for the online inference. There are three key components in this flip model. The first is that is the modality transformation. The modality transformation converts the tabular data features into a textual sentences using the simple templates, preserving the semantic information in the natural language format. And the second is the modality alignment pre-training. It uses a field level masking with MLM, MPM, and ICL for the fine-grained cross-modality alignment. And finally, adaptive fine-tuning jointly trains both models with learnable weights alpha to combine outputs for the CTR prediction. And moving to the experiments, SLEEP demonstrates strong results, as you can see from this table. SLEEP achieves its state-of-the-art performance, outperforming baselines across all categories: ID-based models, large model-based models, and the hybrid models like the CTL as I mentioned before. Other data sets like movie length 1 million, both crossing and Goodreads. The practical values of the flip is that the flip's fine-grained alignment joint MLM and NTM outperforms instance level methods, enabling the meaningful feature level intentions and enhancing diverse ID-based models and pre-trained large models of varying sizes. And I will introduce another subcategory, the embedding subcategory of the modernization. The background is that the sequential recommendation systems predict user preferences through interaction history using learnable item embeddings. The motivation is that the sequential recommendation systems models rank semantic understanding of textual item attributes. And the large models have strong semantics but poor item level distinction of the recommenders. There are two key stages of this method. The first is the supervised contrastive fine-tuning, and the second is the recommendation adaptation training. The large model embedding builds the textual problems for each item by combining tasks instructions with attribute value pairs. Then performs data augmentation by randomly dropping attributes to create two different prompt values as positive pairs, while treating other bench items as negatives. The large model embedding feeds these augmented problems into a large model to extract embeddings and applies the contrastive learning to bring the same item embedding closer while pushing the different items apart. Large model embeddings thus train the large models to encode fine-grained attribute distinctions, resulting in a more meaningful item representations for recommendation tasks. And the large model embeddings address the challenge of high-dimensional large model embedding ranking collaborative filter signals through such an approach. The large model embedding first applies PCA for dimensional reduction, followed by a trainable adapter to transform embeddings for the sequential recommendation system capability. A large model embedding then frees the large models during the trainings and updates only the adapter and the sequential recommendation system backbone using the recommendation loss to learn collaborative signals. Large model embedding finally incorporates the collaborative alignment where the adapters outputs align with the embeddings. From well-trained sequential recommendation system models using a contrastive loss, preventing overfitting while ensuring the embedding capture both semantic understanding and collaborative filtering. Here is the experiment result of large model embeddings. This method pre-computes item embeddings offline to replace the original embedding layer, ensuring zero runtime overhead. The method consistently achieves the best overperformance across the EF Amazon built-in and function data sets. The practical values is that the large models embeddings as CFT and RAT framework bridges the semantic understanding with collaborative filtering, which is very important for the integration of large models and the recommendation systems. This integration enables the efficient pre-computed embeddings and enhances the sequential recommenders without runtime overhead. Another work of the embedding subcategory is the large model initialization, or LM initial. The background is that the collaborative filtering models predict user preferences through interaction patterns, but face a cold start and embedding collapse challenges. The motivation is twofold. The collaborative filtering models, the traditional CF models capture interaction patterns but lack semantic understanding. Language models can provide rich semantics but struggle with item-level distinctions. The two case stages is selective sampling and efficient initialization. The language model initialization bridges the language model CF embedding gaps using the selective initialization with three sampling strategies to transfer knowledge from large embedding to lightweight models. This method extracts k-dimensional embeddings using a variance-based selection for discriminative features and random select for the balanced representation. This approach captures the most informative dimensions while maintaining the comprehensive coverage for the semantic space. Efficient initialization shows the CF models to inherit some semantic knowledge from large model embeddings while preserving the scalability. Models start training from semantically informed states rather than random weights, leading to a faster coverage to the better performance. And here is the experiments part of large model initialization. The large model initialization outperforms the baseline collaborative filtering models across all datasets, with variance-based selection achieving the best results. Using only 0.2 million parameters, it beats large model REC's 7 billion large models while running the 25 to 30 faster than the direct large model approaches. The practical values of large model initialization is that this method provides a free lunch approach for enhancing the collaborative filtering models with large model semantic knowledge while maintaining high efficiency and scalability for the real-world deployment. And another work about the embedding subcategory is learn. The background is that the real-world large model deployment in the recommendation is hindered by a domain gap and catastrophic forgetting. The two motivations is the first is the domain gap. The mismatch. The domain gap means that the mismatch between the large model's open world knowledge and the recommendations collaborative knowledge. And another motivation is the catastrophic forgetting. The fine-tuning large models to their full extent causes them to forget pre-trained knowledge. The two components of this learn method is the first is the content embedding generation, and the second is the preference comprehension. The learn is the Twin Tower framework adapts such two components. The first content embedding generation is that the learn uses frozen large models as an item encoder to convert text into rich content embedding. Freezing is the key to prevent the catastrophic forgetting and preserving pre-trained knowledge. And next is the preference comprehension. The learn employs lightweight trainable transformers and learns user preferences from item embedding sequences. The model is trained end-to-end by contrastive learning. Sorry. And here is the experimental result of the learn. The learn achieves its SOTA performance on a large scale on offline data sets and it delivers a significant business impact in real-world online A/B tests on Kuaishou. The practical value is that the learn is the first large model enhanced solution successfully deployed and missionized in a large model industrial recommendation system, setting a new standard for practical application. Another work about the embedding subcategory is the site. The background is that the large models enhance sequential recommendation models with their generalization ability and knowledge base. The motivation is twofold. The first is that the large model embedded may lose fine-grained item information. Another is that the long token sequences causes efficiency issues. The case stages of this model is also two. The first is semantically aligned embedding learning, and the second is the model acoustic sequential recommender training. The side learns the two case stages. The first stage is the semantic aligned embedding. semantic alignment stage where the item embeddings are learned by projecting the line model generated text descriptions into a shared latent space through a trainable project module, followed by a model acoustic recommendation stage where this pre-trained embedding serve as lightweight, semantically rich input features for efficient sequential recommendation models. This decoupled approach maintains semantic consistency while enabling flexible integration with various lightweight sequential architectures. Here is experimental results of the site. The site enhances both recommendation accuracy and inference speed, demonstrating its practical value in real-world applications, such as Alipay's advertisement system, and proving that the linear models can be effectively and efficiently applied in real-world industrial recommendation scenarios. The practical values of the site is that the site significantly enhances inference efficiency and recommendation accuracy, making linear models more practically applicable in the industrial recommendation scenarios. The another subcategory of the model enhancement is the model distillation. We can also focus on model distillation with the knowledge distillation is a prominent compression technique that transforms the powerful capability of large models into a smaller, more efficient recommendation system models in this scenario. However, the fundamental gap between the discriminative recommendation system models and the generative large models presents challenges for traditional distillation approaches. To address this architecture, the existing studies have developed two main distillation strategies that bridge the gap between the linear models' knowledge and the recommendation system's requirements. The core idea here is to compress the linear model knowledge into a lightweight models that maintain the recommendation quality while achieving the computational efficiency. The two categories, and the first is feature-based. The feature-based distillation transfers the knowledge directly through a hidden state alignment between the teacher linear model and the student recommendation system model, focusing on the intermediate representations rather than the final outputs. Another one is the response-based distillation. The response distillation leverages the linear model generated ranking lists and the recommendation outputs to guide the training for the smaller recommendation systems through a ranking distillation loss. The first feature-based subcategory work is the leader. The background of leader is the leader is used in a medication recommendation system. The background is that the medication recommendation provides a prescription suggestion to doctors. Linear model has two advantages: the medical semantic understanding and code start capabilities. The motivation of this model is twofold. The first is the complex medications names may cause the linear model output recommendations not in a drug databases, leading to failures. The another one is the resource-intensive linear models enhance challenges in the resource-constrained medical institutions to use linear models for the drug recommendations. There are two case stages for the leader model. The first is the improve for the linear models. The leader replaces the original text generation height layer with a new classification layer and fine-tunes the model using BCE loss to enhance the recommendation performance. And the distillation of the linear models. Such a stage is to lighten the inference loads. The leader designs a feature-based distillation process where the hidden state from the final layer of the linear models serve as guidance to distill semantic understanding capabilities into a smaller, more efficient model. In experiments, leader compiled the recommendation results for patients with multiple and single visits. The leader significantly outperformed other baselines across all user groups. And the practical values of the leader is that the leader can be used for recommendation prescriptions for patients who force the visit to the hospital. It means that the large language models and the combination in such scenarios could be good for could start scenarios. Another feature-based method is SIM for REC. SIM REC. The background is large language models have demonstrated exceptional promise in the sequential recommendation, as I mentioned before. The first motivation is the intermediate layers of large language models are largely redundant for the sequential recommendation tasks. And the second is the massive computational and deployment costs make the large language models impractical for the industrial applications. There are three case stages for the SM rack. The first is layer-wise feature distillation. The layer-wise feature distillation allows the intermediate hidden state to transfer rich feature-level knowledge, not just mimic the final output. The second one is the dual-loss feature alignment. The dual-loss feature alignment employs the dual-loss mechanism to match features in both direction and magnitude. And the third one is the auxiliary supervision. The auxiliary supervision applies early task-specific supervision to shallow layers, enabling the efficient learning in a compact model. And in experiments, the SM rack achieves the state-of-the-art performance while reducing the computational costs largely. The practical value is that the SM rack offers the industrial path to harness the power of large models in recommendation system in an economic, efficient, and high-performance manner for using distillation guided stages. And here is the another subcategory of the model distillation of the model enhancement. The response-based method, the DIR for 2 rack. The background of the DIM2 rack is the large model-based recommenders face serious inference in efficiency issues, posing substantial challenges to their practical applications. The motivation is twofold. The first is teacher knowledge reliability. The teacher's knowledge isn't always reliable, as the large model is not always reliable. And the second one is the model capacity gap. The student always struggles to assimilate the teacher's knowledge. And the third one is the semantic space divergence. The different languages between the student and the teacher make direct alignment counterproductive. And there are two case studies for this method: the importance of well-ranked distillation and the collaborative embedding distillation. The DIS2 rack is designed to effectively distill the knowledge from large model-based recommender to the conventional recommenders. The first important well-ranked ranking distillation, the DIL2 rack, introduces important weights to selective reliable knowledge rather than blindly mimicking the teacher ranking. The second one, the collaborative embedding installation, the DIL2 rack performs collaborative fusion to bridge the semantic space divergence between the teacher and the student. Here is experimental results of the DIL2 rack. These results are truly exciting. After distillation, the DIL2 rack's lightweight student model achieves a millionfold speed up in inference time, reducing hours of computation to a mere seconds. Most surprisingly, on several datasets, its recommendation accuracy surpasses the massive large model teacher. The DIM2 rack successfully integrates the semantic reasoning power of large models with the efficient collaborative filtering capabilities of conventional recommender models. The practical value of the DIL2 rack is providing the industry with an economical, efficient, and feasible path to innovation. The DIL2 rack eliminates the trade-off between the performance and the costs, seamlessly integrating the large model power into existing recommender system for significant performance gains for and a fraction of the cost. Okay, next let's move to another. Yuhao will introduce more about the model enhancement.
Okay, I'm ready here. Just a minute, I need to share with my screen. Okay, can you see my screen now?
Yeah, oh, good.
Okay, so let's start. Hello everyone, I'm Yuhao Wang from City University of Hong Kong, and I'm going to introduce the second part of the model enhancement. Okay, so the first group is embedding utilization. And in general, the ARM generates the natural language to complete various tasks. However, the textual outputs are often difficult and inefficient to be integrated into the recommender system models directly. So to avoid the deficiency and better utilize the semantics of ARM, many recent works utilize the embeddings derived from the ARM. For example, the hidden states of the last transformer layer of the ARM to enhance the transitional recommender system, that is the RS in short, as a semantic supplement. And from the aspect that the ARM embeddings address in the traditional RS, this line of work can be categorized into user only, item only, and user and item. And in the cluster of the user only, the ARM is used to generate the representation of the user's preference directly. And the ARM embeddings will then be fed into the traditional RS model for augmentation. And among them, a representative method is to reason about the user preference given its profile and historical interactions. So it is as implemented in the KAR framework, which has already been introduced above. So as shown in the purple box in this figure that, for example, given a user's profile and her interaction sequence, so the ARM needs to infer about her preference. Okay. And afterward, some methods like the ARMCF adopt some advanced techniques like the train of thought, namely the COT, to generate better user embedding. And the overall idea is that, first of all, for the offline service, they fine-tune the ARM to enhance its recommendation capabilities and generate the COT reasoning with collaborative filtering information and construct in-context COT datasets. Okay, so second, for the online service, they retrieve the in-context COT examples, learn the word knowledge and reasoning-guided collaborative filtering feature, and use this feature to enhance existing recommender systems. Okay, so let's take a close look at its framework. By leveraging the design prompt, the ARM aims to generate the COT of the user's decision-making on the target item. So you can see in the red box here, and the aim of this prompt is to generate a COT that considers the several following points, and it needs to generate the COT based on the user history and to infer about the preference and the recommender features here. Okay, so in the offline service, specifically, they perform the instruction tuning on the Llama 2 by data mixing to obtain the CF information about users and items in the recommendation data. And then they obtain namely the RecGen Llama here, which generates the COT reasoning for a subset of examples in the training data, and thus forming the in-context COT dataset. Yeah, and in the online service, the retrieval modular uses a query composed of the textual features of the current recommendation features to perform the embedding-based retrieval on the in-context COT dataset and forming the in-context COT examples. So these in-context COT examples are concatenated with the current recommendation features and then fed into the in-context chain of thought modular of the LRMCF to learn the word knowledge and reasoning guided CF feature. And finally, the enhanced CF feature is fed into the backbone recommendation model for making the final prediction. Okay, so therefore, compared with the previous KR, it has the advantage that the LMCF does not require the real-time generation of new data for the new users or items. Okay, and the authors experiment on different CTR backbones like the DeepFM and DCN on the Amazon dataset, and it achieves the improvement compared with the KAR and other baseline methods. And besides, the second group is the item only. And in some types of the recommender systems, for example, for the sequential recommendation, the item embeddings plays a fundamental role. Thus, most existing embedding utilization focuses on the item-only enhancement. And many early studies in this subcategory directly adopt the frozen LLM without fine-tuning. And for example, the TD-Rec applies Llama 2 or BERT to encode the item text first, and then it proposes a frequency-based fusion with FFT to combine the derived semantic embeddings and the ID embeddings. And finally, the fuse embedding is fed into the sequential recommendation models like the SAS-Rec to conduct the recommendation prediction task. However, these works may lose the informative semantics of LLM embeddings during the training. And another example is PAD, namely the PAD here. And this work is our publication on the CIGAR 2025. And there are two challenges for the alignment plus the SFT in the previous works. And the first is the inability to capture all statistics of the data distribution. And this is because the most common contrastive learning with the cosine kernel is suboptimal according to the reproducing kernel Hilbert space theory. And the second is the catastrophic forgetting in the alignment, because with only one set of the collaborative embeddings, the alignment usually leads to the catastrophic forgetting on the collaborative embeddings. And these are our motivations. Okay, so let's take a look at the framework proposed. And first, the textual embedding is generated from the LLM2vec based on the Llama 3 8 billion. And next, the collaborative embedding is obtained from the SAS-Rec pre-trained on item ID. So in this stage, we simply need to obtain the item embeddings from two modalities. The first is the textual embedding from LLM, and the second is collaborative embedding. And after obtaining the textual and collaborative embeddings, we will align these two embeddings with each training sample. And in particular, we built an alignment expert, as you can see on the right upper bound. And it needs to take both textual and collaborative embedding as input, and we propose to adopt multi-kernel maximum mean discrepancy, namely the MKMMD as the alignment loss with the characteristic kernels explicitly. And it is able to preserve all information about the distribution, namely the distance information between the behavioral item embedding and the target item embedding is important in the sequential recommendation. And in addition, we introduce a binary cross-entropy loss regarding the recommendation label to prevent the collaborative embeddings from the catastrophic forgetting during the alignment. And in the final phase, namely the collaborative fine-tuning phase, besides the alignment expert we use in the second phase, we introduce two modality-specific experts. That is, one takes only the textual embedding as input on the right here, and the other takes the pre-trained collaborative embedding as input, as shown in the left part here. And these three experts are combined through an MOE, namely the mixture of experts architecture through a frequency-aware gating mechanism. Okay, so the overall performance on the public Amazon datasets is shown in the table. And in summary, on all three datasets, our proposed path achieves state-of-the-art performance. And we also validate that our proposed method can mitigate the cold start problem with the ARM knowledge effectively. And moreover, we also plot the L2 distance of each behavioral and target item pair in the collaborative and textual modality. And we plot the results for three baseline methods and our proposed path. Yeah, and the results are shown in the right part and the bottom part. And we can see that compared with the other three methods, PAD succeeds in learning a generally larger textual difference for those item pairs with top collaborative distance, and learning a smaller textual distance for those with bottom collaborative distance. And therefore, we can conclude that the PAD greatly improves performance on the code items with better alignment of textual embeddings towards the collaborative space. Yeah, and next, another contribution of this paper is the first to adopt the Kendall's law to measure the degree of discrepancy or alignment between different embedding space. And we also further illustrate the forgetting issue of the non-anchored loss as the violet line in the figure, and it shows those code item IDs, that is with the bucket from ID from 7 to 10, has their embedding distance distribution more diverged from the original embeddings. And therefore, we have the results that the rec-anchored alignment loss avoids the catastrophic forgetting of the collaborative embeddings and succeeds in aligning the textual embedding towards the collaborative space. Yeah, and also to validate the compatibility of the proposed method, apart from SUSREC, we also experiment on two typical sequential recommendation models as the backbones, as you can see, including the GRU for rec and Kaiser. So we can see that PAD significantly enhanced the performance of the original model on all three datasets, indicating that it acts as a powerful model agnostic enhancement paradigm. Yeah, and we move on to the second paper of the item only. So to address such an issue, the ARM ESR, which is also our publication in our Applied Machine Learning Lab on NIPS 2024, it devises a new pattern of the frozen ARM embeddings with a trainable adapter to maintain the original semantic information. And the motivation of this work is that there are two long-tail challenges existing in the current sequential recommendation models. And the first is the long-tail user challenge So as the figure shows, the majority of users with few interactions receive suboptimal recommendation services. And next is the long tail item challenge. And the histogram indicates that over 70% of the items own no more than 30 interactions, but they are often not well recommended. So these two challenges cause the poor experience for users and less profits of the sellers. And here the LLMs are promising to address them for our semantic review. And here is the overview of the proposed LLM ESR framework, and it consists of two modulars. The first is the dual view modeling, consisting of the semantic view modeling and the collaborative view modeling to address the long tail item issue. And specifically, this modular consists of two branches. The first is the semantic view modeling. It aims to extract the semantic information from the user's interaction sequence. And it first utilizes the semantic embedding layer derived from the LLM's item embedding to encode the items. And then an adapter is designed for dimension adaptation and space transformation. And the output sequence will be fed to the cross attention for fusion and then sequence encoder to get the user representation in the semantic view. And the other branch is the collaborative view modeling, as shown in the blue box here. And it transforms the interaction sequence into an embedding one by a collaborative embedding layer. And next, followed by the cross attention and the sequence encoder, the collaborative user preference is obtained. And at the end of this modular, the user representations in the two views will be fused for the final recommendations. Okay, and the second modular is the retrieval augmented self-distillation, which enhances the sequential recommendation model to address the long tail user problem accordingly. And this modular expects to enhance long tail user through informative interactions of similar users. And first, the derived LLM's user embedding is considered as the semantic user base for retrieving the similar users. And finally, the derived distillation loss will be utilized as an auxiliary loss for training. Yeah, and next is the experiment part for the LLM ESR. First, from the overall comparison, the LLM ESR leads the overall performance, which indicates the better enhancing effects. Yeah, and the second, for the long tail issues, the LLM ESR achieves the best on tail item, which highlighting the effectiveness of the semantics. And besides, this framework can augment them better due to the explicit utilization of the LLMs from the user side. Okay, and next we move on to the next paper. And despite the successful utilization, the general purpose LLM is often not well suited for the recommendation tasks. And so several works propose to fine-tune the LLM before utilization. For example, the Node LLM and Node LLM 2 are both derived for item-to-item recommendation, where the LLM aims to derive the item embeddings for retrieval. So Node LLM here only targets combining the textual semantics and the collaborative signals. And specifically, they first construct a unified node compression prompt for each node sample and then decode through the pre-trained LLMs like Llama 2, and which utilize a special token to compress the node content and generate the hashtags or the categories simultaneously. Okay, and next, the to construct the related node pairs, and they count the co-occurrence scores for all node pairs from the user behaviors and form the set of the co-occurrence scores for each node. And they select the nodes within the highest co-occurrence scores in the set as the related nodes for a given node. And further, to recommend the relevant nodes for each sample, the generative contrastive learning modular, namely the GCL here, utilizes the compressed tokens as the embeddings of each node, and then trains the LLMs to identify the related nodes from in-batch negatives. And simultaneously, they employ the collaborative supervised fine-tuning, namely the CSFT approach, to train the models to generate the hashtags or the categories for each node. And by contrast, the node LM2 gives out a novel path to fine-tune the LM for understanding the multimodal features of the items. And the first component is the multimodal in-context learning. And this method separates the multimodal content into visual and textual components, and subsequently compressing the content into two modality compressed words. And next, the second method of this framework is the late fusion mechanism. And they adopt the multimodal gate fusion mechanism, which takes the visual representations from the visual encoder and representations from the LM to generate the final multimodal recommendations. Okay, and next we move on to the third categories of the model enhancement, which is the user and item. And the current papers can be clustered into two categories. One is to utilize the user and item LM embeddings for recommendation by a similarities function directly. And for example, as shown in this page, the BAHE proposes to partition an LM into lower layers and higher layers, and it uses the lower layers of the LM to encode the item attributes to get the atomic item representation, and then the corresponding comic vectors of the user's interacted items are fed into the higher layer. And meanwhile, different from the direct embedding utilization, the embedding guidance methods only use the LM embeddings as the guidance for training or parameter synthesis. And according to which aspect the LM embeddings aim to enhance, we first categorize the current works of the embedding guidance into user only and user and item. And an example of the user only is the LLM for MSR. And to begin with, we target at the multi-scenario recommendation, namely the MSR in short, and which utilizes the data from multiple scenarios or the so-called domains, like the category of product on the e-commerce platform, to simultaneously improve their recommendation performance and tackles the data sparsity problem. And the typical model structure of MSR is shown in the right part here, and it takes the scenario ID and user features and item features of an instance as input, and the subsequent blue part represents the shared parameters, while the red and yellow denote the scenario specific parameters, and which is similar to the multitask modeling. And however, it is faced with two challenges. The first is insufficient scenario knowledge incorporation. And specifically, the domain indicator is usually the only scenario knowledge leveraged to capture the domain distinction. And the second, the user's personalized preferences across scenarios tend to be ignored. And this is because most MSR models only rely on different parameter sharing patterns and the collaborative information. So therefore, the motivation is to incorporate the LM to improve the conventional RS, and specifically, the LM acts as a reasoner plus the encoder here. Yeah, and the framework generally consists of two steps. The first step is the multi-scenario knowledge reasoning, and specifically, they design a scenario-level prompt to explicitly capture the commonality and distinction of scenarios from their statistics and the semantic descriptions. And besides, they design a user-level prompt to explicitly explore the personalized, common, and distinct interest among all the scenarios from the abundant historical interaction. And the second step is the multi-level knowledge fusion. And on the one hand, the meta networks dynamically generate the meta layers to adaptively fuse the scenario and user level knowledge with the collaborative information in the MSR backbone model. And on the other hand, it proposes a hierarchical bottom plus parallel structure in which the user level meta layers are placed at the bottom while the scenario level meta layers are implemented in parallel to the MSR backbone. Yeah, and the experiment part of the ARM for MSR is shown here. And first, taking star as an example, it achieves increase on all data sets. And the reason for its superiority is that, on the one hand, both the scenario backbone models and baseline methods incorporate insufficient scenario knowledge, that is, the domain ID only, and lack personalized modeling. And on the other hand, it first utilizes LLM to explore domain correlation and infer personalized cross-scenario interest, then integrates meta network to explicitly enhance the multi-scenario modeling capability. And meanwhile, it also enhances the performance of all the backbone models, namely the different multi-scenario recommendation backbone models. Yeah, and finally, as for the user and item line of the guidance research, these studies guide both the user and item representation learning. And for example, the RLM rec kicks off this line, which adds an extra loss to align the collaborative user and item embeddings with the corresponding LLM embeddings during the training. And specifically, they first use the GPT 3.5 Turbo to generate the user and item profile. And then they propose two alignment methods, namely the bidirectional contrastive alignment and generative alignment with the unidirectional reconstruction. Okay, and to sum up, in this part of the model enhancement, we categorize this line into the model initialization, model distillation, embedding utilization, and embedding guidance, as shown in the tree figure here. And the first two categories involve applying the LLM to the entire RS model, while the embedding utilization and guidance only impose the LLM on the embedding layer. Yeah, and the next, Qidong will conclude this tutorial.
Okay, thank you, Yuha. I will share my slides. Okay, hi everyone, I'm Qidong. I will present the conclusion part. To begin with, let me summarize today's tutorial. From our previous session, we can categorize existing LLM enhancement solutions for recommendations into three categories. That's knowledge enhancement, interaction enhancement, and model enhancement. The knowledge enhancement utilizes the word knowledge and the strong reasoning ability of LLMs. This sort of solution typically enhances traditional recommender systems with explicit semantics. The second category, interaction enhancement, relies on the generation ability of LLMs, where LLMs augment the training data with rather implicit or explicit semantics. And the model enhancement uses the strong representation ability of LLMs to enhance recommendation models with implicit semantics. An important motivation for designing LLM ERS methods is their outstanding efficiency compared with LLM as recommender systems, because the enhancement can be kept offline instead of real-time inference for online serving. However, offline efficiency is still an important topic for LLM ERS methods. We next compare the offline efficiency of different categories. The typical of knowledge enhancement involves knowledge encoding by LLMs and further conversion to representations with small language models such as BERT. This process requires the dual encoding of large and small language models, which may require large storage and is hard or inefficient to realize daily updates. The methods of interaction enhancement can be rather efficient as they do not change the training and inference procedures of recommendation models, except for providing augmented interaction data. This implies that they are highly scalable to big data scenarios. For model enhancement methods, they typically rely on the LLM representations. They may encounter pre-encoding and storage issues to prepare, update, and store high-dimensional atom representations with LLMs. However, they can be more efficient than knowledge enhancement methods as they do not require further encoding with small language models and avoid the potential lengthy output problem. To analyze the trends of LLM ERS research, we realize the typical literature on how they use LLM semantics in the vertical direction and the LLM types in the horizontal direction. We also present the enhancement category and whether the LLM is fine-tuned, and mark the time of each solution in this figure. For the semantics, we can find that researchers initially explored the explicit semantics and nowadays focus on implicit semantics, especially the model enhancement solutions, which is in the shape of stars. And for LLM types, open source LLMs that can be fine-tuned for recommendation tasks are more welcomed due to the low deployment costs and high adaptability. Next, we want to share some insights on future directions for LLM-enhanced recommender systems. First, LLM can be extended to diverse recommendation tasks. Existing works have focused on revolutionizing several basic recommendation tasks. They have proven the effectiveness of bringing the semantics of LLM to traditional RS. This indicates that it is also promising to replicate their success in some other recommendation tasks, such as multitask and cross-domain recommendations. In addition, current LLM-enhanced RS relies solely on textual input. How to extend the current frameworks to other input compositions, such as multimodal or text-free systems, might be challenging. For multimodal input, merely replacing LLMs with MLLMs might not be enough. For example, for e-commerce platforms, some products may rely on textual descriptions for fine-grained information, like suitable phone versions for phone cases. While for clothing products, we distinguish different ones mainly based on visual patterns. So, a unified representation from MLLM cannot support adaptive representation. How to build a multimodal LLM-enhanced RS is still an open problem. As for text-free scenarios, it may be associated with tabular data comprehension, especially when most features are continuous values. Another future direction lies in the user-centric enhancement. Current LLM-based user enhancement typically relies on concatenation of item descriptions in prompt, or the integration of enhanced item representations. These methods can lead to the lengthy prompt and behavior-unaware integration. As a result, user-centric enhancement might be a promising direction, which may include item-free user enhancement and behavior-aware item integration. Also, there are still some problems for LLM ERS frameworks. First, compared with LLM as RS solutions, LLM ERS is very efficient. However, for some practical scenarios, it may contain billions of items. It requires lots of computational and storage resources to encode and store item representations with LLMs, which is still impractical compared with traditional RS. In these scenarios, ROI might be limited to deploying LLM ERS. As a result, it is important to develop scalable LLM ERS frameworks. Secondly, explainability is an important aspect of trustworthy RS. LLM is a promising solution to enhance this for RS, but current LLM ERS frameworks do not address this problem. It might be valuable to explore how to generate explanations while enhancing RS with LLMs. Lastly, it is hard to evaluate and compare the effectiveness of LLM ERS frameworks. Current conclusions are based on the integration of LLM enhancement into traditional RS. The effect of solely LLM enhancement cannot be measured. Maybe some specific benchmarks and metrics can tackle this problem. And that's all of our tutorial. All of the materials in this tutorial can be found in the first survey, and the other two surveys from our team may also be useful for you. For the tutorial, if you have any question, please contact me via this email without any hesitate. Besides, you can also scan the WeChat QR code to join our discussion group. All the presenters are in this group. And finally, thanks for your attendance. Hi. Hi, you mute your voice.